Alright guys, this is going to be a quick review of the heat transfer, the material you'll need to know for the remainder of the course. We're just going to look at some of the concepts, actually one concept of heat transfer you'll need when analyzing heat exchangers, which is what the rest of the course is going to be covering. So we'll look at convective heat transfer, and we'll spend a couple minutes just talking about insulation thickness. So the fluid mechanics part of the course is pretty much over, with the exception of your projects, of course. Now in the heat transfer section, we'll look at convective heat transfer, and then we'll apply that theory to practical heat exchangers. We'll look at three types of exchangers: double pipe exchangers, shell and tube, and cross flow heat exchangers. And we're essentially going to analyze them using the theory from a heat transfer course on convective heat transfer. So that's what we're going to review briefly today. So convective heat transfer is heat transfer between a fluid and a solid, as you may recall. So the fluid could be a liquid or air, and then there's two types. There's what's called forced convection, when the fluid is forced across the solid, such as air being blown over a fan or water being pumped through a pipe. This would be considered forced convection. And natural convection is when the fluid is not forced, so still air next to a wall, or water that's not moving inside a pipe. These would be examples of natural convection. So the law that governs the heat transfer, or the flow of heat, either from the fluid or to the fluid, is called Newton's law of cooling, and it's as follows. So heat flow, the rate of heat transfer, is equal to alpha, which is a heat transfer coefficient, which we'll look at later. The area, so this is the area of contact between the fluid and the solid. Okay, so if it's a wall, it's the cross-sectional area of the wall. If it's a pipe, it would be the inside surface of the pipe where the fluid is touching the solid part of the pipe. And then the delta T is the difference in temperature between the pipe and the fluid. Okay? Now the alpha is dependent upon a number of factors, which we'll talk about later, but this equation can also be written as Q equals, difference in temperature over resistance, if we make the analogy of the heat. So this is the fluid on this side, and this is the wall here. And the heat, in this case, the fluid is hotter than the wall, the solid, and so the heat is flowing from the fluid into the solid. This is the temperature of the fluid, TA. T1 is the temperature of the wall of the solid. And so this is like electricity, where you have a current flowing because of a difference in voltage. And so they can make this analogy down here. TA, again, temperature of the fluid, T1 is the temperature of the solid wall, and you have a resistance to that heat flow. So the current going through here is the flow of heat in watts, and you have a resistance, that resistance to the heat flow is essentially the 1 over alpha A. So this equation and Newton's law of cooling are exactly the same. We're just replacing alpha A with this R here. So we know what all these variables are. The question is, how do you find A? Well, as you learn in heat transfer, A is dependent upon a number of factors, and but it's calculated using dimensionless numbers. So the three dimensionless numbers we're going to be using when analyzing our heat transfers are the Nusselt number, Prandtl number, and Reynolds number. Some combination of these three numbers will be used to calculate what the alpha value will be for the double pipe exchanger and the shell and tube and the cross flow exchangers. So these three dimensionless numbers are the ones that are going to be used in order to calculate alpha, and then you can plug in alpha into the other equation to find out the flow of heat. Now, generally speaking, heat transfer problems are of two types. You have those that prevent heat transfer, such as a thermos or a water heater, where you want to insulate it so that heat doesn't escape into the atmosphere. And the second type of problem is when you promote heat transfer, such as heat exchangers. So as I mentioned, the remainder of the course is on heat exchangers. So we'll mention very briefly right now about insulation, and then we'll stop there. So when choosing insulation, i.e. when preventing heat transfer, there's two factors that we have to consider. There's the cost of losing heat into the atmosphere, and the second cost is of course the cost of insulating so we don't lose heat. And if we plot these two, this line here is the cost of insulation, so the thicker, this is the thickness, the x-axis is the thickness of insulation, and the y-axis is the cost. As you increase the thickness of insulation, of course your costs will go up, and as you increase the thickness of insulation, the amount of heat you lose will obviously go down. So if you add those two costs up, you find the minimum cost somewhere where you find the optimal thickness of insulation that you want to use. Okay, so this is just a general overview of the idea that there's an optimal thickness when considering what thickness of insulation to use. But we're not going to go into this. The course is really about heat transfer and not insulation. So I just want to mention this briefly and stop here. So we looked at a review of the equation that governed convective heat transfer, and we looked at the idea that there is an optimal insulation thickness when looking at insulation. So starting next class, we're going to use Newton's law of cooling and the dimensionless numbers mentioned to analyze and size and design heat exchangers for applications. Okay, so that was it for a quick brief review. For those of you who have not taken heat transfer or are not taking it now, you'll probably need a little more than that, so please come and see me during office hours and I'll post more details on Blackboard. Alright? That's it for now, guys. Thanks.